Organic synthesis is, at heart, a toolkit. Master a handful of powerful reagents, and you can assemble almost any molecule you can imagine. Here are 10 of the most important, and the mechanisms that made each one famous. Our first reagent. Anhydrous aluminium chloride, the classic Lewis acid. Its aluminium has only 6 electrons, desperate for a lone pair. Handed an alkyl halide. The chlorine donates a lone pair to aluminium, the carbon-chlorine bond breaks, and we get a tight ion pair. A carbocation paired with tetrachloroaluminate. For a primary halide, a completely free carbocation is an oversimplification. Benzene now attacks the cation. Its pi electrons reach out to form a new carbon-carbon bond, giving a resonance-stabilized rhenium ion. The positive charge is spread over 3 carbons, and the ring has, for a moment, lost its aromaticity. Finally, tetrachloroaluminate removes the proton. The electrons fall back into the ring, aromaticity is restored, and aluminium chloride is regenerated. This is the Friedel-Crafts alkylation. But beware. Carbocations can rearrange, and the product reacts again, giving overalkylation. Acylation fixes both problems. With an acyl chloride, aluminium chloride generates an acylium ion, resonance stabilized across carbon and oxygen. Because it cannot rearrange, acylation cleanly delivers an aryl ketone. Boron trifluoride. Boron has only 6 electrons, so it is an even hungrier Lewis acid than aluminium chloride. It is usually handled as its ether complex. It activates electrophiles by binding to oxygen lone pairs. Coordinate it to an epoxide, and that strained ring is primed to open. A nucleophile now attacks the more substituted carbon, from the backside. The carbon-oxygen bond breaks, and the ring springs open, with inversion of configuration. The pattern is precise. Acid activation gives SN1-like regioselectivity, but the attack itself is SN2-like, from the back. The same Lewis acid also drives acetal formation, the Mukayama aldol, and cationic polymerization. N-bromosuccinimide, or NBS. Its quiet secret is that it releases bromine in tiny, steady amounts, keeping the concentration very low. Under radical conditions, a bromine atom abstracts an allylic hydrogen, the one next to the double bond, giving a resonance-stabilized allylic radical. That radical grabs a bromine, forming the allylic bromide and releasing a new bromine atom to carry the chain. And the key step. NBS plus hydrogen bromide regenerates molecular bromine, but only in trace amounts. Because the concentration stays low, bromine substitutes at the allylic position, instead of adding across the double bond. This is the Wall-Ziegler reaction. Diazomethane. A pale yellow gas, and a beautiful, dangerous reagent. It is drawn with 2 resonance forms, and it carries a perfect leaving group built in. Nitrogen gas. Treat a carboxylic acid with it. The acidic proton transfers to the carbon of diazomethane, making a methyldiazonium ion, and a carboxylate. The carboxylate then displaces nitrogen in a clean substitution, giving the methyl ester. The driving force is simple. The loss of very stable nitrogen gas. It also performs the Arndt-Eistert homologation. An acyl chloride gives a diazoketone, which rearranges through the Wolff rearrangement to a ketene, and adds water to give an acid 1 carbon longer. Powerful, but toxic and explosive. Dicyclohexerbodimide, mercifully shortened to DCC. A dehydrating coupling agent, drawn as accumulated diamide. A carboxylic acid adds across its central carbon, producing a highly reactive intermediate called the oacillosauria. This is the activated form of the acid, and the entire reason DCC works. Now an amine attacks that activated carbonyl, forging the amide bond, and expelling the stable byproduct, dicyclohexylurea. With a catalyst called DMAP, it builds esters 2, the Steglic esterification. DCC is the workhorse that stitches peptides together. Lead tetraacetate. A powerful oxidant with one very specific talent. It cleaves 1920 diols. Give it a cis-diol, 2 hydroxyl groups on neighboring carbons. Both oxygens bind to the lead, forming a 5-membered cyclic intermediate. That ring then fragments. The carbon-carbon bond between the 2 oxygens snaps, and out fall 2 carbonyl compounds, alongside lead 2 acetate. Cis-diols react fastest, because they slot into that cyclic intermediate easily. The reagent cleaves diols just like period 8, a molecular pair of scissors. The Ziegler-Natta catalysts. A combination of titanium chloride and an aluminium alkyl. First, the aluminium alkyl hands an ethyl group to titanium. This creates the active titanium carbon bond, with an empty coordination site right beside it. An alkene now docks onto that empty site, and then inserts into the titanium carbon bond. This is migratory insertion, and the polymer chain grows by 2 carbons. Then it repeats, again and again. Because the titanium center controls every insertion, the chain grows in a perfectly regular, stereoregular way, giving isotactic polypropylene. Coordination polymerization, and a Nobel Prize. DDQ. A quinone engineered to be a ferocious electron and hydride acceptor. Its favorite move is dehydrogenation. DDQ pulls a hydride off a benzylic carbon, leaving behind a stabilized cation. That cation loses a proton, a new double bond forms, and the ring drifts toward aromaticity. DDQ, meanwhile, becomes its reduced form, DDQH2. So it aromatizes rings, oxidizes alcohols, and is the standard reagent for removing the pyrimethoxybenzyl, or PMB, protecting group, while leaving a plain benzyl group untouched. The dithiones, and the elegant trick of umpalung. Normally a carbonyl carbon is electrophilic. Watch us reverse that. Convert an aldehyde into a 1,3-dithione. Now the hydrogen sitting between the 2 sulfurs is unusually acidic. Remove it with butyllithium, and that carbon becomes nucleophilic. An acyl anion equivalent. Its polarity has flipped. The sulfurs stabilize the negative charge through their polarizability. It now attacks an alkyl halide, and a simple hydrolysis, with mercury 2 chloride, unmasks a ketone. This is the Corey-Seebach reaction, joining carbons in a way nature normally forbids. The Merrifield resin. Tiny beads of chloromethylated polystyrene, and the foundation of solid-phase synthesis. Anchor the first amino acid to a bead. Its carboxylate displaces the benzylic chloride, forming an ester link to the support. Then repeat a simple cycle. Deprotect the nitrogen end, couple the next amino acid using DCC, and wash away every impurity, simply by filtering the beads. Finally, cleave the finished peptide from the bead. The exact conditions depend on the linker and protection strategy. BOC with hydrogen fluoride, or FMOC with trifluoroacetic acid. It earned a Nobel Prize. 10 reagents, 10 transformations. Lewis acids that forge carbon bonds. Selective halogenation and methylation. Coupling agents and oxidative scissors. Polymerization catalysts, dehydrogenation, polarity reversal, and synthesis on a bead. Together, they are the working vocabulary of the molecule builder. Learn what each one does, and the whole language of organic synthesis opens up.